Okay, so my name is Shweta. I am pursuing Masters in Computer Science and I'll be graduating this May. Let's see, today's session is on linear algebra. So this session will be recorded and there is a lot of topics to cover, so I might go a bit fast, so pay attention. And let me know if you are not understanding a particular part and you want me to go over it again. So I'll start sharing. Okay, so first we'll go through the preliminaries. In linear algebra, we need to know what are the basic objects which are frequently used and what kind of operations can be performed. So we'll start with scalars. I'm sure everyone knows what scalar is. It is a numerical quantity. So in 52-degree Fahrenheit, the value 52 is a scalar. A scalar can be represented using a single tensor element. So we can see the code snippet here. X is assigned the value 3, Y is assigned the value 2, and you can perform addition, multiplication, subtraction, division, x to the power y. And when you see here, the shape is 1, which means it is just giving one tensor element. And all these operations will output single tensor element. Okay, we'll see what tensors are going ahead. What's a vector? A vector is a list of scalars. So, for example, if we initialize x to range 4, so x will take the values 0, 1, 2, 3. So this is a vector. A vector can be a row vector or a column vector. Vectors can be accessed, elements in the vector. So 0, 1, 2, and 3 are the elements in the vector. So vector elements can be accessed by giving the position, the ith position. And the position in a vector starts with 0. So when we try x of 3, so the third position, 0, 1, 2, 3, it will return the value 3. Yeah. Length, dimensionality, and shape. For a vector, all these terms mean the same. It means the number of elements present in the vector. So in the previous vector that we saw, the number of elements present were 4. So the length of x is 4. We can use x dot shape too. It will return 4. So what's the difference? Here it returns the number of elements. Here it returns the number of elements for every axis, because in TensorFlow we store vectors in tensor. We will see what tensor is, so you will understand what the axis means. In vectors, dimension, length, shape means number of elements in the vector, but in tensors it means the axis. What are matrices? Matrices are basically generalization of vectors. So vectors can be represented using one-dimensional tensors, and matrices require 2 dimensions. We need to specify the number of rows and the number of columns to represent a matrix. So this is how you represent a matrix. Range 20 means the values in the matrix will go from 0 to 19. 5, 4 means this matrix has 5 rows and 4 columns. How do you access elements in a matrix? To access elements in a matrix, you just have to provide the row and the column position. So if you try to access 0, you will do A of 1, 1, which means first row, first column. Now, transpose of a matrix. What is transpose of a matrix? Transpose of a matrix is basically flipping the axis. That is, you will write rows as columns, and you will write columns as rows. For example, if this is a matrix A, then all you have to do is flip the rows and columns. So you will write rows as columns and you'll write these columns as rows. So this will give you transpose of the matrix. What is a symmetric matrix? A symmetric matrix is basically when you take transpose of the matrix, it will give you the same matrix. So if you see here, B, it's 1, 2, 3, 2, 0, 4, 3, 4, 5. And if you take transpose of B, it will still give you the same matrix. And you can check it by doing B is equal to transpose of B. Every value will be returned true. And the data type will be Boolean. I'm sure you guys know Boolean means true or false. It takes two values. So if the matrix would not be symmetric, then at least one of these values would have been false. Now, since all are true, it means that the matrix is symmetric. Tensors. Now, this is an important concept because in TensorFlow, everything is represented using tensors. So what is a tensor? Tensor is basically n-dimensional array with arbitrary number of axes. Okay, so let's see. This, when we say x has a range of 24, means the values taken by x will range from 0 to 23. It has two axes. You can see this is one axis and this is the second axis. Every axis has 3 rows and 4 columns. So this is a tensor. So in tensor, when you add two tensors, you add element wise. So you add the first element of tensor A to the first element of tensor B, the second element of tensor A to second element of tensor B, and so on. So the addition, also the multiplication in tensors are element-wise. So when you do element-wise addition and element-wise multiplication or any element-wise operation in a tensor, the shape of the tensor does not change. So the shape of A is 5, 4, 5 rows, 4 columns. The shape of B is the same, 5 rows, 4 columns. After doing A plus B or A minus B or A into B, the output tensor will have 5 rows and 4 columns. Now, what is reduction? When we do element-wise operations in tensor, do not change the dimension, right? In reduction, we will change the dimension of the tensor. We will change the shape of the tensor. So let us look at this using an example. So consider this is a tensor A. If we do reduce sum, what it basically does is it adds every element present in the tensor A. So it will add 0 plus 1 plus 2 through 19 and will give you a scalar value of 190. Okay, so what if you want to keep at least one dimension same, which means you want to keep either the number of rows same, the row dimension same, or you want to keep the column dimension same. Then you specify axis. So reduce sum across axis of 0 means you will keep the row dimensions intact. You will be reducing the row dimensions. So there are 5 rows. Now, how do you reduce the row dimension? You will add 0 plus 4 plus 8 plus 12 plus 16, and that will be your first element. 1 plus 5 plus 9 plus 13 plus 17, that will be your second. So you can see now the number of columns has been kept intact, but the row dimension changed. If you specify axis equal to 1, it will keep the row dimension same and it will compress the column. So you will do 0 plus 1 plus 2 plus 3, 6, and so on and so forth. So if you look at the code snippet here, for axis equal to 0, you'll see that the shape, the columns have been kept intact, but there is no row dimension present. Similarly, for axis equal to 1, the number of rows have kept intact, but there is no column. Remember the shape because when I go to non-reduction sum, I will be showing you the shape where you can compress along the row or along the column, but there will be dimension. So here in non-reduction sum, if you compress across the columns, it will keep the number of rows same, but there is also a column element present. It shows that there is one column, but there are 5 rows. So this means that we have kept the dimension. There are row and column dimension same. In reduction sum, we basically compress 2D to 1D. And here we are keeping the 2 dimensions as 2 dimensions. What is a dot product? A dot product is basically summation of all element-wise products. So for 2 tensors, what will be the dot product? 0 into 1 plus 1 into 1 plus 2 into 1 plus 3 into 1. This will be the dot product. Now the dot product is same. You can use a tensor dot, the tensor dot function, or you can use reduce sum over x into y. So x into y will do x multiplication, and it will take a summation of all that. Both will return the same answer. What is a matrix vector product? So we'll look at this using an example. So a matrix, let us consider a matrix B, a vector X, which has values 1, 2, 3. So how do you take a matrix and vector product? You take a dot product of first row with the vector X. So it's 1 into 1 plus 2 into 2 plus 3 into 3. That will be your first element of B cross X. Dot product of second row with the vector will be your second element. Third row with the vector will be your third element. So a matrix into a vector will give you a vector. What is a matrix multiplication? Consider 2 matrices. So how do you multiply a matrix? You do dot product of first element, first row with first column. You'll get the first element of B cross C. For the second element, you'll do first row into the second column. Third element, first row, third column. So basically, you will multiply every row with every column to get elements of the matrix. A matrix multiplication will in the end give you a matrix. And you have to make sure that the number of columns in B has to be equal to the number of rows in C. What are norms? Norm basically tells you how big a vector is, the length of the vector. Okay, you can think of it as a distance. So there are certain properties to a norm. So the first property is if every element in a vector is scaled by a factor alpha, then the norm will also be scaled by the factor alpha. That is your first property. The second property is the triangle inequality. We might have seen this in Pythagoras and all. So if two vectors are added, then the norm of f of x plus y will always be less than or equal to f of x plus f of y. And the third property is pretty simple, that the norm should always be greater than or equal to 0. You cannot think of distance as a negative value, right? So in order for the norm to be 0, every element in the vector should be 0. Only then you will get the norm of a vector as 0. So L2 norm corresponds to the Euclidean distance. What does L2 norm do? It squares all the elements in the vector, adds them up, and takes the root. So that is the L2 norm or the Euclidean distance. In TensorFlow, you can simply use the norm function and it will return you the L2 norm. Now, sometimes we also use the L1 norm in data science. It is basically summation of all absolute values. Okay, so basically you'll take absolute values of every tensor element and you do a reduced sum. This formula generalizes the L1 and L2 norm. So if you put P as 1, you'll get L1 norm. If you put P as 2, you'll get L2 norm. For a matrix, the norm is called the Frobenius norm. So basically, it squares all the elements in the matrix, takes a summation and the root. That is the Frobenius norm. So you can simply call the norm function and pass your matrix, and it will give you the norm of your matrix. So these are the preliminaries. We go on to our main topic. Geometry and linear algebraic operations. So we saw what a vector is, right? It can be represented using one-dimensional tensor. It can be a row or a column vector. How to access the elements of a vector, we know that. Now, we can also think of vector as a point in space. Consider this 1, 2. It is a vector or a direction. So consider a line. Think of a line with joints from the origin pointing to 1, 2. So it can be a direction or it can be a location. So this vector basically tells us that this point is 1 step to the right and 2 steps up. So the tensor can be a point in space or a direction or a location. So this is another example. This vector basically just tells that this point is 3 steps to the right and 2 steps up. This is an identity of a vector. So consider 3, 1 as u, 1, 2 as v. What is u minus v? We know in vectors it is element-wise operation. So 3 minus 1 is 2, 1 minus 2 is minus 1. So when you plot it, this is the 2, minus 1 vector. When you shift it parallelly, you will see that u minus v is indeed a vector pointing from v to u. So this is an identity where u is equal to v plus u minus v. Every vector satisfies this identity. Now, we saw what a dot product is. It is summation of all element-wise multiplication. Where is dot product used? Dot product can be used to find angle between two vectors. Okay, so if we need to find the angle theta between two vectors, we use dot product. So we'll see using an example. So let v be a vector of length r parallel to x-axis, and let w be a vector of length s which is making an angle theta with v. So when you make a projection of w on v, what will it be? Using trigonometry, you know it is s cos theta. So basically this length of projection w on v is s cos theta. So what is v dot w? It is length of v into length of the projection of w. It is r s cos theta. What is r and s? R is length of v, which means norm of v. S cos theta, s is length of w, which means norm of w. So you can represent it in this format. Okay, so when you keep theta on one side and bring everything else on the other side, we'll get theta equals to arc cos, means cos inverse of v dot w upon norm of v into norm of w. So here's a code snippet. How do we find theta? Dot of v and w divided by norm of v into norm of w and an arc cos of the entire thing will give you the theta. Okay, so what is cosine similarity? Cosine similarity basically tells you the direction of two vectors, how similar they are. Okay, So in the above equation, if we keep cos theta on one side, then we see that cosine similarity is v dot w upon norm of v into norm of w. Cos theta takes a minimum value of -1, a maximum value of 1, and it is 0 when the angle is 90. So when two vectors are perpendicular to each other, cos theta will give you 0. When the two vectors are pointing in the same direction, cos theta will be 1. When two vectors are opposite, means the angle is 180 degrees, cos theta will give you the value -1. Where is cosine similarity used? So in deep learning for text analysis, we use cosine similarity. We represent the text using vectors, using encoding, and then we check how similar to text is. So cosine similarity can be used there. What is a hyperplane? A hyperplane is generalization of a line to higher dimension. What does this mean? What is the use of a hyperplane? So consider a plane, a sheet of paper passing through the diagonal of your room. So basically this hyperplane will cut your room into two parts, right? One is the part above, one is the part below. This is used for classification purpose. In machine learning algorithms, deep learning algorithms, you will see that you compare a point with a hyperplane and see where it lies. So we can decide if point A lies in class 1 or class 2. So for example, consider we a vector W 2, 1, and we want to find points V that satisfies this condition, W dot V equals to 1. Okay, so you know what is the dot product of W and V from the previous one. It's norm of V into norm of W cos theta. And we want this to be 1. We know W vector, so we can find the norm of W, which is root of 2 square plus 1 square, which is root 5. So we know that V cos theta should be 1 upon root 5. Now what is V cos theta? V cos theta is projection of V on W vector. So this length is V cos theta. So we know that the points whose projection is 1 upon root 5 will satisfy the above condition. And when you plot all these points, you will realize that it is a line perpendicular to the W vector. So basically what happens is this line, all points that lie on this line will satisfy W dot V equals to 1. All points that lie on left will show that W dot V is less than 1, and all points on the right will satisfy W dot V is greater than 1. You can see it in this diagram. So basically this line here in 2 dimension becomes your hyperplane. For 3 dimension, it's the same. So consider there's a W and we want to satisfy the same condition, then you'll realize that every point that satisfies the V dot W equals to 1 condition lies on a plane. Everything to the left of the plane is less than 1, right of the plane is greater than 1. And this is used for, as I said, classification purpose. Geometry of linear transformations. What is it? So this is a vector, this is a matrix A. We want to see how a matrix applied to a vector affects the vector. Okay, so we'll do A into V. We saw how to do a matrix under vector multiplication, right? We get this value. We take X as common, AC, Y as common, we write this as BD. So what is this? If you solve it, it is A into the vector 1, 0 plus Y times A into the vector 0, 1. So what does this equation exactly tell you? It tells you that we can identify how a matrix, when applied to a vector, will change the vector based on how the matrix affects the vector 1, 0 and 0, 1. Let's take a look at this with an example. This is a matrix A, 1, 2, -1, 3, and we want to see how it affects the vector 2, -1. So we'll just put it in the above equation, which means 2 times a of 1, 0 plus minus 1 into a of 0, 1. It will give you 2 times 1 comma minus 1 minus 2 comma 3. So basically, the vector a when applied to 1, 0 and 0, 1 changes the vector to 1 comma minus 1 and 2 comma 3. So here you can see that the matrix is changing the vector. It is basically rotating and scaling the vector. Okay. Now sometimes when a matrix applied to a vector, it causes tremendous change. Usually a vector can only skew, rotate, or scale the grid. It does not change the structure of the grid. But sometimes a vector, consider this B vector, when it is applied to the above, a B matrix, when it is applied to the above vector, it changes into one dimension. Okay, so you can see that if you apply it, it will be 2 times 2 comma 4 minus 1 comma minus 2. If you plot 2 comma 4 and minus 1 comma minus 2, you will realize that they lie on the same line. Okay, so basically what B matrix is doing, it is converting the 2 dimension to a single dimension. A line is a 1D, so it's converting the 2 vectors into a single dimension. Now we'll see the reason why. Why is applying matrix B doing that to the vector? The reason is linear dependence. You can clearly see that B1 is minus 2 times B2. It means B1 is dependent on B2. Okay, so you can represent it as B1 equals to minus 2 times B2. And you can represent a matrix as sum of columns of the matrix. So B can be represented as some constant A1 into B1 plus some constant A2 into B2. Okay, and when you like substitute B1 equals to minus 2 B2 in this equation, you will get this A2 minus 2 A1 equals to B2, which means B1 is redundant. B1 depends on B2, right? So what this generalization means is, if you want to find if there are linearly dependent vectors in a matrix, you need to find coefficients A such that they are not 0. And if there is even a single coefficient A which is non-zero, it means that there will be a vector which is linearly dependent on the other vector. Okay, and if there exists linear dependence in a matrix, then the operations performed by that matrix cannot be undone. Okay, so finding linear dependence is pretty difficult because you'll have to take a look at every subset, right? So what is a rank? The rank is basically the largest number of linearly independent vector in the matrix. Okay, so here if you see B, you can see B2 is twice of B1, right? Which means B2 is dependent on B1, which means there's only one linearly independent vector, which means the rank of B is 1. By looking at a particular matrix, it is difficult to say what the rank of the matrix will be. So there are several methods with which you can find out what the rank of a matrix can be. So I'll show you just one method. So this is a normal method. It is a very simple method. What this method says is, try to make as many diagonal elements 1 and all the other elements below it, that's in the same row and in the same column, 0. And you can use any row or column transformation to achieve this. So consider this matrix C. The first diagonal element is already 1, so we do not have to make any transformation. So now our aim is to make everything below this 1, 0. So what we see that this minus 1 plus 1 will make it a 0. So R2 will change to R2 plus R1. R3 is already 0, so we'll keep R3 as it is. R4 will become R4 minus 2R1. Doing that, we'll get every element below this 1, 0. Now, you cannot just subtract the first element, right? You'll have to do the same for the entire row. Okay, and you'll have to fill in the matrix. Then the second step is to make every element in the same row 0. So we see that C2 will be C2 minus 3 times C1 to make it a 0. C4 will remain the same. C5, column 4 will be column 4 plus column 1. And column 5 will remain the same as it has already a 0 here. So after doing this transformation, we'll get everything as 0. When you keep on iterating this, you make this 3 as 0, and then you make this 3 as 1, you make these as 0, you make these as 0. When you keep on doing that, you will in the end get this matrix. What can you see here? There is only 2 diagonal ones. All else has become automatically, right? So what does this say? This says that the rank of this matrix is 2, and rest of the column vectors are dependent on these 2 column vectors. This is what rank says. So where is this linear dependence and rank used? It is used in invertibility. So as I said, matrix A, if there is linear dependence in it, then the transformations done by the matrix cannot be undone. Okay, so how can you invert a matrix? How can you undo something that has been done by a matrix? You will find its inverse and you will multiply it with its inverse. So A into A inverse will give you an identity matrix, which means that inverse undoes everything that has been done by the matrix A. So what is an inverse for a 2 cross 2 matrix? Flip A and D and negate B and C, divided by the determinant of this. We'll see what a determinant is, but a determinant for a 2 cross 2 matrix is A into D minus B into C. Okay, so you can see that when you multiply a matrix M with its inverse, you'll get an identity matrix. Okay, we usually do not use inverse because it has a lot of computation, a lot of memory space involved. So we avoid using inverse. So that is a numerical issue with using inverse. Even if we can get the previous matrix, like here you can see matrix A applied to vector X gives you a vector B. And if you multiply it with A inverse, you will get the previous original vector X. But this requires a lot of computation. So it is a lot of time consuming process. So we usually avoid using inverses. What is a determinant? A determinant is basically, previously in linear transformations, we saw how applying a matrix A was changing the grid, how it was affecting the vector. Here, the vector, this plane, it changes from a square to a parallelogram. To find the area of this new plane, we can use determinant. Okay, so determinant for a 2 cross 2 matrix is A into D minus B into C. And in Tensorflow, you can use the determinant function, the linear algebra determinant function. Now, for a 3 cross 3 determinant, we'll just look how a 3 cross 3 determinant looks like. So the determinant for a 3 cross 3 matrix is A into the determinant of EFHI matrix minus B into the determinant of DFGH matrix plus C into the determinant of DEGH matrix. So I'm just showing this, but we have a function in TensorFlow to calculate determinants, so we won't be using these formulas a lot, but just to give you an idea of how a determinant for a 3x3 matrix would be found. So we saw how to do multiplication of two vectors, which is element wise, multiplication of two metrics. So for multiplication of tensors, we need to provide indices. We need to give it certain specifications, certain rules about which dimensions should be equated and all. And there is a lot of computation in mathematically if you look at how to multiply two tensors. So I will not be going into this in depth because I don't think we'll be using a lot of mathematical computation when it comes to tensors. We can directly use TensorFlow functions. But just in case you guys want to know more about it, you can maybe ping me, email me. We will go to Eigen Decompositions. So I just wanted to quickly ask you guys, did you understand what I have taught till now? Do you guys have any doubts?
One question. Are the matrix and tensors almost the same?
Yes. So you can say that a matrix is a tensor with just one axis. So in tensors, so what makes a tensor different from a matrix is tensors you can give several axes, you can give several specifications. Okay, wait, let me show you a code snippet. So this is how you define a tensor, right? If you did not put this 2, this would be a matrix. Okay, it would be a 3x4 matrix. But we are giving that the tensor has two axes. This is the first axis, this is the second axis. So since we are specifying the axis, a tensor becomes a matrix. And as I told you, when we use TensorFlow, everything is represented, vectors, matrices, tensors, everything is represented using tensors. So vector is a one-dimensional tensor, matrix is a two-dimensional tensor, and in the tensor itself, the tensor will have several axes. That's the only difference. Is it clear?
Yes.
Okay. Does anyone have any other doubt? No? Do you guys want a 5-minute break or should I just continue and get over with it?
Continue.
Continue? Okay.
I have a question.
Yeah, sure, go ahead.
What's the difference between the vector and the array?
A vector and an array. So it basically comes to, when it comes to a structure, they both are the same. But when it comes to coding, a vector is dynamic array. So when you keep on inserting values in a vector, it will keep changing its size. Okay, and an array has a fixed size. But when it comes to a structure, both are the same.
Okay,
Yeah,
thank you.
yeah. Okay, so should I move on to the next topic? Okay, so this is Eigen Decompositions. So what is Eigen Decomposition? Basically, you can represent a matrix as a eigenvalue and an eigenvector. You can represent a matrix in terms of its eigenvalue and eigenvector. What are eigenvalues and what are eigenvectors? If you apply a matrix A, okay, to a vector V, you will get some vector, okay? But sometimes when you apply a matrix to certain vectors, there will be change in only specific dimensions. Some of the dimensions will not change. For example, if you apply matrix A to vector 1, 0, it will give you 2, 0. So basically, the vector 1, 0 is being stretched only in the x dimension. The y dimension remains the same. Similarly, if you apply A to 0, 1, it will give you a 0, -1 vector, which means the x remains same, but the y is being stretched. Okay, so such vectors, when you apply to a matrix and there is only particular changes, not everything changes, something remains unchanged, such vectors are called eigenvectors. And the value by which it is stretching, in this case 2 and -1, these values are called your eigenvalues. Okay, so when you have an eigenvalue and an eigenvector, you can write this equation. A into V is equals to lambda into V, where lambda is your eigenvalue and V is your eigenvector. Okay, now let us see an example of how to find eigenvalue and an eigenvector. Here, we have been given a matrix A, okay, and there is a vector V, which is the eigenvector, and we have to find out what it is, and we need to find lambda, which is the eigenvalue. So what you can do is you can find the determinant of A minus lambda I should be equal to 0. By solving this, you will find the values of lambda. Okay, so substitute A, lambda into I is your identity matrix. You will get lambda 0, 0, lambda. Element-wise subtraction, you will get this matrix. When you take a determinant, what was determinant of a 2 cross 2 matrix? 2 minus lambda into 3 minus lambda minus 1 into 2 is the determinant, will be equal to 0. When you solve this polynomial equation, you will get lambda is equals to 4 and lambda is equals to 1. So these are your eigenvalues. Now, how do you find your eigenvector? You simply substitute the lambda value in this equation. AV equals to lambda V. So A into V is equals to lambda. Our first lambda is 1 into V. And the second equation will be A into V will be equal to a second lambda, which was 4 into V. Now, when you solve this, you will get the equation y equal to minus x and y equal to 2x. Okay. When you put the value of x equals to 1, you will get the value of y is minus 1. When you put the value of x as 1 here in this equation, you'll get the value of y is equals to 2. So these two vectors, 1, minus 1 and 1, 2 are your eigenvectors of the matrix A. Okay, so you can see this. You can use a linear algebra eigenfunction in Tensorflow to find out the eigenvalues and eigenvector. So this is your eigenvalue 1 and 4. Here it is represented as a complex number, and this is your eigenvector. Okay, decomposing a matrix, as I told you earlier, a matrix can be represented in terms of its eigenvalue and eigenvector. So let W be the eigenvectors of matrix A.
Sorry for interrupting. I just have a question. In the other one, why did you give x is equal to 1?
Where?
In the example.
Oh, in the example, so we are taking the minimum value, okay? So now we kept x is equals to 1.
Just to confirm, the eigenvector is v and lambda is the eigenvalue, right?
Right.
So I understood the rest of the thing, but why did you give, see, we found y is equal to minus x and y is equal to 2x, but why did you give x is equal to 1?
Yes, so I'll tell you. So once you keep x equals to 1, you'll get 1 comma minus 1. If you put x equals to 2, what will happen? You will get 2 and minus 2, right? So what is it? It is just a stretch. It is a vector is being just stretched by a factor, right? You are just multiplying. When remember I told you the identity, where if you change every value in a vector by some factor, its norm, its length will also change. So basically you are just multiplying 2. If you put x equals to 2, if you put x equal to 3, you are basically just multiplying the vector with 3. You can take the 3 common outside, right? You are just changing the length of a vector. So we are taking the minimum value. We are taking value as 1. You can take value as 2 too. You can take value as 3. But what will happen? You are just stretching the vector. You are just multiplying the vector with a factor. So in case you take value as 2 here, you will get 2 comma 4 as your eigenvector. What have you done?
So just giving the minimum.
Yeah, we are just taking a minimum value.
Okay, thank you so much.
Yeah, no problem. Okay, so your W is your eigenvector. So the columns in W will be one vector, one eigenvector, and the second column in W will be your second eigenvector. Okay, and sigma represents the eigenvalues of A. That is the diagonal elements of sigma. So 1 is your lambda 1, 4 is your lambda 2. Okay, so we remember the formula AV equals to lambda V. Here your V is W, lambda is represented by sigma. Substitute it. When you multiply throughout by W inverse, that is inverse of your eigenvector, you will get the matrix A. So this is how you represent A using its eigenvalue and eigenvector. Okay, and a matrix is invertible if the determinant is not 0. Only then the matrix is invertible, because when we saw an inverse, we saw inverse of 2 cross 2 matrix. It is divided by the determinant. The determinant cannot be 0. Only then a matrix is invertible. Okay, so what are the operations that can be performed using eigen decomposition? Imagine you need to find out A raised to n, multiplying a matrix A n times. Okay, so you can represent this A matrix as W sigma W inverse. Write it n times. You will realize that there will be like consecutive W inverse and W, right? So those two will negate each other, because we learned A into A inverse will give you an identity matrix. So W into W inverse will give you an identity matrix. So which is basically negating what W has done, right? So all the W and W inverse in middle will get cancelled. So what remains is n times the sigma, n times the eigenvalue, and the first W and the last W inverse. Okay, so just in case we want to find A inverse and you have the eigenvalue and the eigenvector, all you need to do is the eigenvector into the inverse of eigenvalue into inverse of the eigenvector. So this way you can easily kind of find out A inverse, or A square using eigenvalues and eigenvector. And if you have eigenvalues, you can easily find determinant of A by multiplying every eigenvalue. So the formula for determinant of A will be product of every eigenvalue of A, right? When we saw determinants, we saw that finding a determinant for a 2x2 matrix is easy. For a 3x3 matrix, we saw what it was, A into determinant of a small 2x2 matrix, B into, and so on. So as the size of A increases, computing determinants becomes more and more complex. So if you have the eigenvalue for A, then you can just find determinant by multiplying all the eigenvalues. Okay. Now, next is eigen decomposition for symmetric matrices. I told you earlier when introducing matrices that a symmetric matrix is a matrix where the matrix and its transpose is the same, right? So A and A transpose will be the same. So for such matrices, if you find out the eigenvector, you take a transpose and you find out the inverse of the eigenvector, you will notice that they both are the same. So W transpose and inverse of W transpose will be the same. So in the above equation of A equals to W sigma W inverse, instead of finding inverse, obviously it is pretty easy to find transpose. So you can represent the matrix, the symmetric matrix A as W sigma W transpose. Okay, because like when I was talking about inverting a matrix, I did tell you that inverting is a complex task. It takes a lot of computation. You have to find the adjoint of matrix A, then you have to find determinant, then you do adjoint upon determinant to find the inverse of a matrix. So finding a transpose is pretty easy, obviously. You just need to flip the axis. Okay. Now, I've been talking about eigenvalues and eigenvectors from so long, but looking at a matrix A, we cannot say what the eigenvalue will be, okay? So this theorem, the Gershwin circle theorem, it gives you an idea of where the eigenvalues will lie, what will be the range of eigenvalues for a particular matrix, okay? So consider this matrix A, and let there be R, okay, and R is a radius of a disk. Consider a disk, okay? So how do you compute R? R is summation of every element along the row except for the diagonal element, okay? So R1, that is R for row 1, will be 0.1 plus 0.1 plus 0.1, 0.3. R for row 2, do not calculate this diagonal element. So it will be 0.1 plus 0.2 plus 0.3, which is 0.6. Similarly, R3 will be 0.1, 0.2 plus 0.5. It's 0.8. And R4 will be 0.1 plus 0.3 plus 0.5, which is equals to 0.9. So what this theorem states is, every eigenvalue of this matrix A will lie in this range. A11 minus R1 and A11 plus R1 will be the range of your first eigenvalue. What is A11? Is the first element, the first diagonal element of your matrix. The second eigenvalue will lie in the range of A22 minus R2 and A22 plus R2. A22 is your second diagonal element, and so on. So we know that lambda 1 will be in somewhere between 0.7 and 1.3. Lambda 2 will be somewhere between 0.4 and 3.6, and so on. So when you calculate the eigenvalue by passing the matrix A, see, these are the eigenvalues. It's 0.9, and 0.9 lies between 0.7 and 1.3. 2.97 lies between 2.4 and 3.6. 4.95 lies between 4.2 and 5.8. And 9.08 lies between 8.1 and 9.9. Okay, so this theorem gives you an estimate of where the eigenvalues can lie. Okay, the next thing is applications. I've been talking so much about eigenvalues, eigenvectors. Where is this used other than just for representing a matrix, using them? In real life, in neural networks, where is this used? So in neural networks, you can consider that a vector is passed through several layers of transformation. Okay, and those layers are basically matrix. I'm not sure if you guys have heard that every neuron in the neural network has a weight assigned to it. So what is the weight? The weight is a matrix that is assigned to the neural network. So when we input a vector to the matrix, we multiply the vector with the matrix. So, and we pass it through several layers. It's not just one or two layers. So we pass it through, maybe depending on the computation, maybe through 5, 6, 10, 20. So you keep on multiplying A, the matrix A, with the vector for n number of times. Okay, so this is a code where you are just initializing your A matrix. And there is also a concept of set seed in TensorFlow. And in fact, I'll just show you a code snippet in MXNet. Here you can see that they have set a seed with some value. So what does this do? This is also available in TensorFlow. You just have to do tf.random.set_seed and give any random number. So what does this do? This basically ensures that every time you run the code, the value of matrix A will be the same. Okay, so consider I did not set the seed and I initialize a 3x3 matrix. The first time I run the code, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9. But it is possible that I stop it and I rerun the code the second time. The matrix can change. It can be 12, 14, 15, 16, 17, 18, 19, 20. So to ensure that every time when we run the program, the A matrix remains constant, it has the same value, we set a seed. Okay, now for our example, what we are doing is we are initializing a Gaussian matrix, a phi cos phi Gaussian matrix. So the mean is 0, variance is 1. I'm not sure if you guys attended yesterday's recitation, but he might have told you about standard normal distribution. It is the same as Gaussian distributed matrix. Okay, so for mean 0 and variance 1, the Gaussian matrix values will range from minus 2.5 to plus 2.5. Okay, we have initialized the matrix here. Then we will see that when a matrix is applied to a vector, it is multiplied to a vector. We saw initially that the vector can be stretched, it can be skewed, the grid can be rotated, and so on, right? So basically, when A stretches a vector too much, the length of the vector becomes very long. What will happen is small, tiny changes in the input will create drastic change in the output. So like think of a couple of pixels, you change a couple of pixel values in a t-shirt, and instead of the predictor predicting it as a t-shirt, just because there is minute changes in the pixel value, it gives you a false prediction of a trouser maybe. Okay, so that is how, if A stretches the vector too long, will affect your prediction. If A shrinks the vector, then no matter what your input is, your output will be some random value. The output will not depend on the input. Okay, so here we have taken a random input vector, multiplied it 100 times with the matrix A, and you can see after about 90 iterations, the vector length, the norm of the vector, is growing uncontrollably. Okay, so basically the vector is being multiplied by a certain factor and the length of the vector keeps on growing. There is no stable state, no equilibrium is achieved. So when this happens, your model accuracy will be affected. Okay, so we don't want this condition. When you find out the quotient and when you plot the quotient, basically the stretch factor by which every iteration the vector is being stretched, you can see it is 1.97. So it means that the vector is being stretched by almost a factor of 2. So if the vector size was initially 2, it became 4, then again it became 8, and so on and so forth. So in order to avoid this, in order to avoid the uncontrollable stretch of our vector, in order to make our vector reach an equilibrium, a fixed length, we normalize the matrix A. Okay, I will tell you by what we are normalizing this. So we are normalizing it with the largest eigenvalue of A, which is also called as the principal eigenvalue of A. And when you do that, multiply this normalized matrix A with the vector, you will see that after certain iterations, the length of the vector is stabilizing. You'll see that maybe after say 10-20 iterations, the length of the vector, if it has reached 10, then after 10, basically it will remain for like till the end of the computation, it will remain the size 10. So this is what is being shown in this graph. So what is a principal eigenvalue? Okay, so principal eigenvalue is the largest eigenvalue of the matrix. Here, how do you find eigenvalue of a matrix? For a vector, we remember the formula, what we did, determinant of A minus lambda I equals to 0. That is how we used to determine the eigenvalues mathematically. For Tensorflow, we will use norm to determine eigenvalues for a matrix. So basically what a norm is, if you remember, it is length or absolute values of every element in the matrix. A matrix has real and complex part, right? So previously I did show you that when we were printing the eigenvalues for a matrix, it was printing in terms of complex numbers, real plus something of j. Okay, so for a matrix, to calculate the norm, you will have to take the norm, consider the norm for both real and complex values. So when you plot it, when you find the norm of eigens for a matrix, and when you sort it, you will get certain number of eigenvalues. And this largest eigenvalue for a current matrix is 4.173 something. This is called your principal eigenvalue. And in order to let our vector reach equilibrium state, keep it stable, we need to normalize our A matrix with this. And once we do that, we will get a normalized vector, a stable vector. So I think the conclusion states the same. The stretch factor remains the same. It is basically, it's being normalized. The conclusion let's read the conclusion. After normalizing the matrices by principal eigenvalue, we see that the random data does not explode as before, but rather eventually equilibrates to a specific value. And this is what we want. So this ensures that small changes in input does not have drastic changes on our output. And also the output is not completely independent of our input. Okay, so I think that's it actually for the day, and we have some time for doubts. You guys have any doubts? Anyone? No doubts?
Will the video be posted on Canvas?
Yes. The session's being recorded, so it will be posted.
Great. There's a lot of material that was covered, so that'll be very helpful. Thank you.
Yes, thank you. So does anyone have anything? No doubts. Did you understand everything? Do you want me to go over any particular part, any particular section? Okay, since we have time, I want you guys to go over this exercise, like solve this first sum and tell me what the eigenvalues and the eigenvectors are. I'll give you until 12:20. Yeah, till 12:20. Find out the eigenvalues and the eigenvector and tell me the answer, or else tell me if you're not able to solve it. Remember the formula for eigenvalues. It's determinant of a minus lambda I equals to 0. And for eigenvectors, once you find the lambda, a equals to lambda v.
So to remove eigenvalue and eigendeterminant,
Sorry, I cannot hear you. Sorry. Can you repeat it?
uh, to calculate the values, first we need to remove the determinant of the vector of this matrix, right?
No,
So
it is a minus lambda I. After doing that, you will get a matrix and you have to find out the determinant of that result matrix. First, you need to do a minus lambda into I. And you're finding the value of lambda.
I still didn't get how to do.
You haven't understood? Should we
No.
solve it? Okay. Solve it first. Look at it. So basically what our matrix is, it is 2, 1, 1, 2. What we need to do is determinant of this matrix A minus lambda times I. So what will lambda do? Lambda inch. Okay, so what you need to do is you need to find determinant of this entire thing and equate it to 0. Okay, so which is determinant of this matrix 2, 1, 1, 2 minus, what is lambda I? I is our identity matrix. So when you multiply lambda with identity matrix, you will get lambda 0, 0, lambda. Now, determinant of this entire thing you will do element wise subtraction. This is your first matrix minus your second matrix. So when you do element wise subtraction, you get 2 minus lambda . 2 minus lambda, 1 minus 0 is 1, 1 minus 0 is 1, 2 minus lambda is again 2 minus lambda. And you need to equate this to 0 again. What's the determinant? Determinant is 2 minus lambda into 2 minus lambda minus 1 into 1. So that is your determinant. So 2 minus lambda into 2 minus lambda minus 1 into 1 is 1 equals to 0. Okay, so when you open this up, how do you multiply two brackets? 2 into 2 minus 2 lambda minus lambda into 2 minus lambda into lambda, which is lambda squared. So it will be 4 minus 2 lambda minus 2 lambda plus lambda square minus 1 will be equal to 0. Okay, so when you solve this polynomial equation, okay, which is basically lambda square minus 4 lambda plus 3 equals to 0. When you solve this polynomial equation, you will get the value of lambda equals to 1 and lambda equals to 3. Did you understand this part till here? How we found the eigenvalues?
Yes.
Yes? Okay. Now since we have our eigenvalues, we will insert it in AV equals to lambda V formula. So what is our A? A is the matrix 2, 1, 1, 2. V is what we have to find. So it is a vector x comma y, let's assume, and we will find the values of x and y. A into V is equal to lambda. Our first lambda is 1, so it will be 1 into this vector x into y. When you solve this, now I told you a matrix and a vector multiplication, it will be 2 into x plus 1 into y will be your first element. So your first element will be 2 into x plus 1y. Your second element will be 1x plus 2y, which is equal to x into y. Okay, now how do you solve this equation? It is basically 2x plus 1y equal to x. And 1x plus 2y equal to y. Okay, so when you take x to one side and y to the other, you will realize both these equations give you the same thing, which is y equals to minus x. Keep y here, take x here, gives you y is equals to minus x. Even for this equation, take y this side. Now, again, all you need to do is substitute value of x to get y. So when we put the minimum value of x equals to 1, you will get y equals to minus 1. So your first vector, your first eigenvector will be 1 comma minus 1. Now we did for lambda equals to 1. Similarly, if you do for lambda equal to 3, this side will be the same. Here it will be 3x and 3y. So it will be 2x plus y equal to 3x and 1x plus 2y equals to 3y, which will give you the equation y is equals to x. So if you put the value of x as 1, you will get the value of y as 1, which means your next eigenvector for lambda equals to 3 will be 1 comma 1. And this is your eigenvalue and eigenvector. Okay, did you understand this? Have you guys understood it?
Yeah.
Yeah, I'm
So
getting a
see,
feel of it.
y equals to x came similarly as y is equal to minus from the second equation.
The second equation?
Yeah. Y equals to x. How it?
Yeah, so like if we solve it for lambda equal to 3, we will get,
Okay, got it.
you'll get 3x and 3y over here.
Yeah,
Just keep x and y on one side. Okay, so I think we are almost at the end of our section. This numerical, you will have to solve using the Gershwin theorem. You can try it out and let me know if you have any doubts. Okay, I think that's it, right? Does anyone of you have any examples? I mean, want me to solve any kind of numerical or have any doubt? Then I can go over it, or else the session is over for the day. No doubts? No, nothing?
Okay, thank you for your time, Shweta.
Yes. Thank you so much. You guys can leave. Thank you so
thank
much.
you.
Thank you. I
Have a
really
wonderful day.
appreciate
Bye.
this
Thank you.
introduction.
Have a great day. Bye.